All right, I guess we can get started now. So thanks everyone for coming to the second CHEP seminar of the semester. We have Derek Ruri who's joining us. Derek received his PhD in economics from the University of California, Davis. He is now a postdoctoral researcher at the Harris School of Public Policy at the University of Chicago. He's a labor economist who specializes in the economics of education, in particular in K-12 and higher education policy. He already has an R&R at the awesome Journal of Human Resources, and today is going to speak to us about class rank really early in life and its potential long-run consequences. Derek, thank you so much for spending your day with our faculty and students today.
It's been an absolute pleasure. Thanks so much for having me. Yeah, just the conversations I've had with people and asking questions, and yeah, it's been really productive for me talking about my research and others' research. So yeah, thanks so much for having me. And let me go to full screen view here. And yeah, so as Joe said, this is going to be focusing on kindergarten. And I want to preface this presentation by saying this is in relatively early days. So if people have any recommendations or suggestions about anything I present here, or perhaps things that come to mind that can be added to set of analyses I'll be presenting here, please don't hesitate to
and just to be clear, Derek, sorry, I should say this at the beginning, that we will just sort of interrupt if folks have questions. We'll just sort of jump in. You don't have to monitor any chat rooms or anything like that.
That sounds great. Yeah, people should feel free to interrupt at any point. So yeah, the title of the presentation today is going to be Putting Decay in Rank. I'll be talking a lot about rank, defining it, talking about the effects of rank and how it works in kindergarten. And I'll be tracing out the effects of rank long-term educational outcomes, which I'll talk about in a bit. But the big kind of 10,000 foot view I want to take before we get into the specifics is to really ingrain in everyone that these rank effects that I'm going to be defining and talking about are real and they're meaningful. So kind of defining what I mean when I say rank effects, this is going to be, where do you rank? What's your ordinal rank within your school cohort? And previous literature has defined what a cohort is in a different way that I'll be defining it. But just imagine a group of students either in the same school or the same classroom, and we'll think of that as the cohort. And the rank effects will be, depending on what your ordinal rank is, how does it impact your subsequent educational outcomes? So it might be hard to believe, but these rank effects have been shown to not only affect short-run outcomes, but also long-run outcomes. There's literature that shows it has impacts on the likelihood that you graduate from high school, whether or not you go to college, what type of college you go to, what you major in, and even your earnings after you graduate. And typically the current state of the literature is the main mechanism that this is operating through is higher rank creating more confident students. And the flip side of this is that a lower rank is depressing students' confidence. So a big theme that I think we all need to grapple with, that I've talked with several people about today, is that we've chosen to educate students in groups, and ranks are naturally going to be a feature of these groups. And in a world in which these rank effects exist, we have to grapple with them and take them seriously. So the other big group of facts I think we need to keep in mind is that early life impacts are extremely important. They're going to be important in the moment for the child. They're also going to be important in the sense that they're going to influence a lot of subsequent decisions and impacts. And we also can't forget that when thinking about the impacts of early life decisions and investments, we can't just be looking where it's easiest to find things. There's going to be things that we have to like really dig to find, like cognitive skills or perceptions of ability and of oneself. So we know that rank effects are strong, but we don't currently know when they begin. And this is true because of two reasons. There's a lack of data on how we can actually rank students early in life, and also kind of biologically or physiologically, we don't know how these rank effects are operating within young students and young children. So we don't really have a good sense of what the mechanisms are early on in life driving these rank effects. So I also want to say kindergarten is a good place to think about seeing whether or not these rank effects exist. So it's often the first time that children are grouped together. So according to the National Center for Education Statistics, between a third and a half of students don't attend preschool, which means the first time they're going to be interacting with a group of peers is going to be in kindergarten. And that this is actually more likely for children of low-income parents. So kindergarten is a good first step in thinking about when we might see these rank effects popping up. Importantly for policy, kindergarten is often the first time that they're really regularly going to interact with the state or some agency that's acting on the behest of the state. And therefore, this is the first time that we can think about using policy to influence these rank effects. So this is going to lead me to my research question is, do rank effects occur in kindergarten cohorts? And if so, what patterns do they exhibit? And by patterns, I mean for what subjects, for what types of students, and what types of circumstances. So my approach is I'm going to study the results from the Tennessee STAR project, which is an extremely famous study in social science history, and I can describe more later. But first, I want to describe the advantages of this approach and how it relates to answering my research question. So the first main advantage of using the STAR project is that students are assessed in kindergarten, which is, I would say, the first barrier in really pushing back to early life to study these rank effects. And they're assessed both in math and reading. I also have, or the STAR data have data at the classroom level, whereas in the past, typically cohorts are defined at the school level using large administrative data sets. This is going to give me access to both student and teacher level data to study mechanisms. A major feature of the STAR experiment is that students are randomly assigned to classrooms, and that's going to give me a big advantage when zeroing in from the school level to the classroom level to rule out potential endogenous classroom formation. The STAR data also have really great long-run educational outcomes, including assessments in grades 1 through 8, high school outcomes like GPA, graduation, and really important entrance exams into college like the ACT. And also it's going to have a battery of measures of non-cognitive skills to study potential mechanisms. So a preview of my results, I find that kindergarten rank has a linear effect on long-run academic performance. And I'm going to put this in terms of decile ranks in your kindergarten classroom. So going from the 10th rank to the 20th rank with the higher ranks, meaning you're a high performer. An increase in decile rank in your kindergarten cohort is going to lead to a 1/10 decile increase in the overall universal 8th grade distribution. So increasing by 10 rank points in your kindergarten classroom is going to increase your overall place in the distribution of 8th grade scores by 1/10 of a decile. It's also going to have a meaningful effect on college entrance exam test taking and performance. It's going to increase whether or not you take the ACT or SAT by 12 percentage points, and it's going to increase your overall ACT score by 0.05 standard deviations. I'm also going to find that it has impacts on high school GPA and graduation. There's also going to be importance heterogeneity by gender and race, which I'll talk about later. But the big takeaway here to keep in mind is that these rank effects are going to be most important for white male students, less important for female students, and less important for Black students. The teacher data that I have, as by virtue of the STAR experiment, are going to allow me to show that there are going to be important student-teacher race interactions. I won't be talking about this a lot today, but there are important results along student-teacher race interactions. And also there's going to be some mild evidence for the policy-minded people that increasing teacher qualifications are going to mitigate these rank effects. And lastly, I'm going to test an important mechanism in the rank literature, which is that these rank effects are driven primarily through ability tracking. I'm going to find that that's not the case.
Hey, Derek,
So
can I ask a question?
Yes.
Hey, in that ranking literature, they always talk about this differences between like ordinal and cardinal ranking. With your results, like you're saying, like a 1/10 of a decile improvement, but do you also look at like how far you are from the top of the class or the bottom of the class and what those effects have? Like, hey, I know I'm like, at the bottom. Does that have more of an effect on me as opposed to if I was closer to the top? Can you kind of talk about that?
Yeah, so I have not yet performed heterogeneous treatment effect by whether or not you're below or above the median. All I can talk about today are these linear rank effects that are, and I've done some robustness checks to show that this rank effect is pretty linear across the distribution, but I've yet to do a formal heterogeneous treatment effect looking about what's the rank effect if you're below the median and what's the rank effect if you're above the median.
Okay.
I suspect, given the robustness checks I just mentioned, that the effect's going to be linear, so there won't be much there, but I'll leave that to future tests. That's a great question. So again,
Eric, sorry, I have a
yeah.
follow-up. Do the parents know the full distribution of test scores?
These exams, my understanding is that it's not common for kindergartners to be assessed in general. And I don't know what the state of kindergarten assessments were back in the 80s, but these, I don't get the sense that parents were aware of the results of these exams. So, and again, these exams are going to be proxies for the ability distribution. I mean, so a parent can interact with the school, can pick their kid up, see the other kids in the classroom, and get a sense of, oh, my kid seems, they're brighter than the other kids. But not only do I not have any data on that, but it seems like that's going to be a very imprecise. There's going to be a lot of measurement error in what parents know about where their kids in. The parents are going to have beliefs about that, but whether or not they actually know is a different question.
Do just again, so I understand what how you're thinking about these test scores, sort of picking up the ability distribution. I'm just I'm just curious about who knows about the kid's score relative to the full distribution. Does the teacher know? Does the principal know? Are there any agents that have this information in front of them?
I think the contrast between, especially with kindergartens, the contrast between what the parent knows and what the teacher knows is strong. I would say the parent has a very, very vague sense, that's be my guess, relative to the teacher. The teacher is with the kids every day. The teacher inevitably is going to know not only the distribution of ability, but I wouldn't be surprised if there's some way that the way the teacher interacts with the children is going to accentuate or mitigate those things. I'll provide some evidence that teacher qualifications are going to be important for mitigating these rank effects. So that leads me to believe that the teacher is not only aware, but potentially doing things differently for kids, not based on their score, but where they rank within the classroom. Those are great questions. I'm going to push back our knowledge of the rank effects to a very early age 5 and 6 in kindergarten. This is going to be the first time we're going to see rank effects not within a school, but within a classroom. Also going to think about, as Joe just pointed out, we're going to see how teachers fit into this rank effect process. I can compare classroom rank effects to what's typically done in literature, which is looking at rank effects at the school grade level. And I'm able to test really important mechanisms by virtue of having access to the STAR data that previous literature has not been able to.
So I have a quick question. So
yeah.
How much is rank just determined by the age of the child? So I know a lot of parents think about when to start their child in kindergarten, and I think implicitly, or maybe explicitly, they think about rank as a reason to delay their child starting. So how does that relate to what you're looking at here?
That's a great question. So I haven't used the STAR data to test the hypothesis that parents are delaying entry. All I know is the previous literature looking at the STAR data has shown that that's not typically true, and other rank papers have shown that parents don't exhibit this type of delay process based on rank effects. And I'll show, yeah. So parents aren't thinking about, is my kid going to be the big fish in the small pond, and making decisions based on that. That's a result from previous rank literature. I've yet to test that here, so that's something I could potentially do. So going forward, there's a couple big buckets of literature that I think we should keep in mind when going over the rank effects I'll present today. So there's the literature that studies both elementary school rank on long run outcomes and high school rank on long run outcomes. The elementary school rank is, there's 2 papers written by Murphy and Weinhardt, and the second paper adds a third co-author, Jeff Denning. What they're going to use in the first paper is data from England, virtually the entire universe of elementary school students. They're going to create the rank based on age 11 exams, and they're going to take a look at the effect of age 11 rank on age 14 exam performance. They're going to find very similar linear effects as what I find here. The subsequent paper uses data from Texas to not only look at further outcomes, but they're going to push the rank effects earlier on in life. They're going to look at 3rd grade exams, which are typically when students are 8 and 9. They're going to look not only at elementary school performance, but they're going to look at high school performance, whether or not they go to college, what type of college they go to, and the labor market earnings they experience after they graduate. And again, they're going to find linear rank effects pretty much across the board along all these outcomes. So those are early elementary school ranks. The high school rank literature is also going to show that even if you rank students as they enter high school, they're experiencing a new cohort, they have a new rank. We're going to see linear rank effects on graduation, whether or not they go to college, as well as whether or not the students exhibit risky behaviors. So I'll be referring to Denning, Murphy, and Weinhardt as DMW, and Elsner and Isfording as IE when talking about my results and how they compare to the previous literature. So a little bit about Project STAR. So it's an extremely famous social science experiment. This was initiated by then Tennessee Governor Lamar Alexander, who ran on a ticket about the importance of education, and was designed by some researchers, signed into law by the legislature in Tennessee, and it was designed to study the effects of class size on learning. So it was initiated in the 1985-1986 school year, so it's quite a long time ago. But the big kind of takeaway is that over 6,000 kindergartners, I think across 76 schools, were randomized within their schools to different classroom environments. And another important feature of the STAR experiment was that these students were supposed to remain in their classroom type up until 4th grade. So over the years, the original researchers collected data about exam performance in grades 1 through 3, and then other scholars then appended those data with state of Tennessee assessments, as well as other measures of academic achievement, and then other scholars then later added on ACT scores, as well as IRS data. So as I said, this is an extremely famous and well-studied experiment that's been used to study really important education topics. Effective class size was studied famously by Kruger and then amended by Chetty et al., looking at the labor market effects of class size. Also, student-teacher race interactions were studied using the STAR data, as well as the effect of disruptive peers. I also want to point out here that all of these studies perform their own balance assessments to show that students are actually randomly assigned to kindergarten classrooms. I'll provide some evidence on that as well. So as I kind of touched on briefly before, there are major advantages to using the STAR data when studying the effects of rank. So the big one is that I'm going to get these assessments in kindergarten, which is 3 years before our currently understanding of when these rank effects start. And it's going to give me assessments in 2 different fields, both math and reading, to see if there's any differences in effects based on those subjects. It's going to give me classroom data. I'm going to get actual classroom assignments, and I get important data on teachers. So the mechanisms I'm going to use when using the data on teachers are their experience, how many years they've been teaching, what their qualifications are, and their race. I'm also going to get these long series of exam results from grade 1 through 8, SAT, ACT scores, high school outcomes, measure of non-cognitive skills. And also importantly, when I zoom into the classroom level, I need to make sure that there's no endogenous classroom formation, and students being randomly assigned to peers and teachers as part of the STAR experiment is going to ensure that that's the case.
Hey, Derek, another question on that. Do you have measurements of their non-cognitive scores in kindergarten, like to be able to assess like the big 5, like grit and things like that?
Not those in kindergarten. I'll talk a little bit about the non-cognitive skills, what they actually are and when they're assessed in a bit. But essentially, it's going to be measures of effort, whether or not they value school, what their initiative is, and what their perseverance is. And I think those are measured in 4th grade and 8th grade.
Okay.
So there's currently no, this is a question that Joe asked me earlier. Do we have any sense, can we collect data, or do we have data at the kindergarten age that might tell us what's going on with rank? And unfortunately, it's very hard to get those data from kindergartners in general for many reasons, not the least of which that they're very potentially difficult to work with. So along with the advantages of the STAR data, there are some disadvantages. The previous papers studying rank have used extremely large data sets, including millions of observations. This is a much smaller sample. This also took place almost 4 decades ago, which might have implications for how relevant it is today. I don't have college and labor market outcomes, which are an important part of the rank story. And importantly, there is infamously significant attrition out of STAR over the course of the study period. I can only really address this last item. So what I can say is that attrition is not related to random assignment into classrooms. This has been shown by previous papers, but in my setting, attrition is related to class rank. So at the end of the presentation, I'm going to go through a few ways to talk through how I deal with that problem. So a little bit about the data. So the first set of data collected by the Project STAR folks was a set of achievement tests, the Stanford achievement tests in both math and reading. And this was done in kindergarten through 3rd grade during the primary part of the research project. I'm also going to have student level demographics, including race, age, and gender, and whether or not they lived in a urban setting, suburban setting, or in the inner city. I'm also going to get teacher level data like race, years of teaching, highest degree earned, and qualifications. Then after this first wave of data was collected, other researchers from the Lasting Benefits Study added Tennessee's comprehensive test of basic skills. This is what I'll be using for my first set of analyses, looking at subsequent tested performance in 8th grade. They also added these measures of non-cognitive skills. So Alex, your question, we have measures of effort, value, initiative, and discipline. These measures are driven or derived from teachers' assessments of the student. So, and they have a whole index of which these four measures are going to be an index of several sub-indices here. And again, these are elicited from teachers in both 4th grade and 8th grade. Then Kruger and Whitmore and Scheisenbach studied the effect of class size on SAT, ACT taking, and this was added to the public use file at that point too. Other scholars then added high school course outcomes like GPA and high school graduation. So this comprises the whole set of the public use files for the STAR project that I'll be analyzing today. So here's a bit of the descriptive statistics. So in this column here, this is all the students for whom there's a valid kindergarten math score. And in column 2, this is for all the students for whom there's both a valid kindergarten math score and an 8th grade math score. So we can instantly see that there's about 40% of the sample has left, or we lose about 40% of the sample when we condition on having both a kindergarten and 8th grade score. Some of these variables are going to exhibit differences across these samples. I'll say most strikingly, you have fewer free reduced lunch students. You have more white students, fewer Black students. And this is going to represent, I think, in some way, this relationship between attrition and rank that I address later in the presentation. And also this is to confirm that there's really not a lot of attrition based on whether or not you're assigned to a small classroom. So this is a diverse population studied in Tennessee, representative of that area at the time. Okay, so moving on to rank and how I'm going to define and study the rank variable, it's based on 2 assumptions. The first is that there is this distribution of ability within a classroom. The second one is that this ability can be captured to some extent by test scores or outcomes of assessments. So this is going to apply that your classroom ability rank can somehow be captured by your test score rank. So I'm going to create one's classroom percentile rank in both reading and math by taking the ratio of your test score or your ordinal rank based on your test score divided by the number of test takers in your classroom. This is going to be my primary explanatory variable. And again, this is for all students in kindergarten, and I create both a math rank and a reading rank. So moving on to identification, typically papers in this literature have relied on idiosyncratic variation in rank. This is variation in parents not strategically sending their kids to different schools or advocating for their kids to be assigned to certain classrooms based on these potential outcomes of rank. And they essentially, it requires a selection on observables assumption, and that there's no selecting into schools based on these rank effects. In this paper, I don't have to make that assumption because the STAR experiment is going to randomly assign students to classrooms. So I can essentially, and this randomization is happening within schools, so there's no selecting into schools. And this is also going to rule out endogenous classroom formation. So more specifically, this random assignment to students is going to ensure that the distribution of potential outcomes conditional just on your test score is going to be equal if I include that rank variable. Including that rank variable is not going to change your potential outcomes. There's no selection into classroom environments for which I'm ranking students over. So here's a graphical illustration of two ways in which changes, variation in rank can occur when you condition on a student's test score. So I want to give credit where credit's due. This is taken from Elsner and Isfording, their paper. The first example over here is where you have the same variation in ability, but you have different means. So you have a student here whose ability here in this classroom, they're in the second quartile, but here they're in the third, because we have mean ability differences between these two cohorts. Here, in this example, these two cohorts have the same mean ability, but they have different variance in ability. So this student here is going to be in the second quartile with a high variance, but with a low variance where it's more pressed together, this student's going to be in the top quartile. So this is a way to show that when you condition on a child's rank, you are going to observe this variation, or when you condition on a child's test score, you are going to observe this variation in rank when you look across different classrooms or different cohorts. So here, this is the distribution of the D-mean math score plotted against the actual classroom math rank. So there are a couple ways to look at this. One way, if you want to condition on a child's score and take a look at the variation in rank, you would just kind of go up this vertical direction. You can see here that, let's take this person here. This person starts at percentile rank of 0.20. And given this score, you can go all the way up to 0.6. So there's a lot of variation in rank conditional on a student's score. It's actually, there's more variation even higher up here. Yeah, so this is an illustration using actual data of how much variation we can get in rank conditioning on a child's score. And this is the identifying variation I'll use to study the rank effects. So moving on to estimation. So this is my estimating equation. So I'm going to include here, so like I said before, rank is going to be a child's rank in different subjects in their classroom is going to be the main explanatory variable. I'll be looking at several outcomes. Here's a function of a student's ability. And I'll assume for my primary analyses, I'm going to assume that this is a linear term in that child's test score in that subject. So when studying the effects of the student's math rank, I'll include a linear term of their kindergarten math score. Later in the paper, when I discuss robustness, I'll be changing this function to include potential nonlinear effects of one's ability on outcomes of interest. Also, I'm going to include a vector of student characteristics that we discussed before: gender, age, race, where their neighborhood is. This is also going to capture a lot of teacher characteristics as well, including class size. And also, this is going to be school fixed effects, as well as mean classroom scores in both math and reading. So this is going to be school and classroom fixed effects, and standard errors are going to be robust clustered at the classroom level.
So, and sorry if you end up repeating yourself, because I know a form of this question was either asked by Alex or Jake. I think it was Alex, and it's about the, I guess, nonlinearities and the effects potentially of what have the less well-identified studies found with regard to, or have they explored this sort of much about, at what sort of thresholds at which this, might matter more. I guess I'm just thinking about, I understand when you're showing the variation picture. I mean, if you're in kind of the mushy middle, I mean, how much does it matter if you're, if there are sort of small differences in rank and sort of the heart of the distribution versus I guess I'm thinking of the tails where you've got, a math score, whatever, of 0, and you're at the top, at the very top in some, versus being in the mushy middle. as compared, yeah, you see what I'm sort of getting at. I guess maybe this is also getting at mechanisms, I guess, about how, how much can I perceive or is the teacher if it's the teacher treating sort of differences among people who are roughly the same, one sort of slightly better versus kind of those more dramatic situations.
Yeah, I think you're getting at a really important point, which I think underscores the power of this kind of identification strategy, is that you just see like these very dramatic differences in rank conditional on test score. But I see your point. It seems like there might be you wouldn't expect a child with this rank, with this score, to have the same effect from rank from this child with this score. And yeah, all I can say is typically, I'll be talking specifically about just linear effects of rank, and on test scores in particular, whether it's the Denning, Murphy, and Weinhardt, or the Elsner and Isfording, they find almost perfectly linear rank effects on test scores. For outcomes such as whether or not you go to college or what type of college you go to, I think there are some non-linearities in these rank effects. For example, I can think of papers that show that lower ranked students, some subset of lower ranked students, are more likely to go to college because they're going to community college than students in the middle of the distribution. So there's some non-linearities in some outcomes in these treatment effects. Yeah, I don't have any results from this project here to talk about potential nonlinear effects. But
it's helpful to hear you sort of talk about the margins on particular outcomes where we might where other studies have found sort of stronger evidence. I appreciate that.
Yeah, and I'll talk about some student level characteristics that show that these effects aren't as strong for certain students, but that's also going to be in a linear way. At least I'll only be able to show results that tell a linear story. Using these data, not only can I do my answer to Alex, I can take a look to see whether or not there's nonlinears based on being below or above the median in rank. That should be pretty simple, but there might be some interesting interactions between teacher race and student race that explain whether or not we're seeing benefits at the upper end of the distribution while muting the negative benefits at the lower end of the distribution. Unfortunately, I don't have those things today, but those are all within my means of being able to do. Okay, so here's estimating equation. That's going to include school fixed effects. It's also going to control for mean classroom scores to make sure we're capturing the ordinal rank and not cardinal rank. And standards are importantly going to be clustered at the classroom level. So the outcomes I'll show first are going to be test scores in 8th grade. I'll show for both math and reading. And what beta is going to represent in the next table is going to be, as I described earlier, it's going to be a decile increase in your kindergarten percentile rank, and the causal effect of that decile increase in your kindergarten rank on your percentage, your rank point place in the overall 8th grade distribution of test scores we see in the data. So this is common in the STAR literature, is to use when looking at the Tennessee CBST outcomes, is to not have the outcomes, the test scores in normalized standard deviation units, but to put it into percentile ranks within the entire distribution. It's also good for comparability with other rank studies because it's typically used in the rank literature as well. I'll also be presenting results for high school GPA overall and by subject. I have results for highest level of math, ELA, and science, and the likelihood that you're going to graduate. Also, the likelihood that you take the ACT and scores overall in math, reading, and writing. I won't be presenting these non-cognitive measures today. The major takeaway is that there's not much evidence for the whole sample that any of these non-cognitive measures change as a function of rank. So despite the fact that they are in the STAR data, there's not much evidence that there's any causal effect of rank on any of these measures. And this might be due to the fact, as I mentioned earlier, these are teacher elicited measures of these non-cognitive skills, which might induce some measurement error, some other issues. So all I want to do is just say that STAR data, and it uses them, other papers in the STAR literature use these measures, but unfortunately I can't detect any causal effects of rank on these measures. So what I want to do here is show you this first column here is going to be your kindergarten reading rank. The second column is going to be your math rank. And all of these rows are going to be different outcomes where, yeah, just the Y variable is going to change. So focusing on your kindergarten reading rank on your 8th grade overall rank distribution, this is saying that if you increase a decile in your kindergarten rank, which is your cohort, which is going to be your classroom, you're going to increase 1.7 rank points in the overall 8th grade distribution. Similar effects for rank on math on reading, similar ranks for reading and math on math distribution. Here we have significant effects of reading on high school GPA, reading rank on high school GPA, but not necessarily for math rank. This is going to be a common theme when we talk about robustness and attrition. The math rank loses out to the reading rank is one of the takeaways of this, at least when it's measured at the kindergarten level. Both kindergarten reading rank and math rank are going to predict an equal effect on the likelihood that you graduate from high school. They're also going to predict whether or not you take a college entrance exam. Reading rank, again, is going to have a strong effect on your overall composite score, but not your math rank. Not surprisingly, your kindergarten reading rank is going to cause an increase in your ACT English score, as well as your math score. And somewhat surprisingly, your math rank is actually related to, this is not significant, but it predicts a negative effect on your ACT math score.
Sorry, can I ask a quick question?
Sorry?
Can you hear me?
Yeah.
So I'm wondering how detailed is your age variable for those kindergartners? Do you have them at the year level or the year months?
Sorry, I couldn't quite hear that.
I'm wondering, can you hear me now?
A little bit, yeah.
Yeah, sorry, my mic is a little bit messed up. I'm wondering how detailed is your age variable? So do you have them at the months or at the year?
Yes.
Because
Yeah,
those kindergartners, they came in, at a fairly young age. Several months away could make a huge difference. So I'm wondering how much of this rank will capture the maturity based on maturity.
Yeah, so there's two responses. So the first is, this is controlling for your actual performance in kindergarten. So to the extent that age has any impact on rank, it must be through your performance on the exams. I'm creating these rank variables based on your performance on these assessments. So any effect that age is influencing that must be through performance on the exams, and I capture that. But I also include an indicator for age. The STAR data does have month of birth, but I think in these regressions, I just have whether or not you are, it's an indicator for whether or not you're in the upper half of the age distribution. I can think about adding some other terms to capture these age results. But again, if these age results are influencing results, they have to be doing it through test scores, which I control for in this regression.
May I ask you a question?
Yeah.
Are these ranked separately, or are they in the same regression, reading and math?
These are separate regressions. That's a great
Right,
question. Yeah,
right,
these are
okay.
individual regressions, right? Yeah. When I combine the both ranks in the same regression, these effects are still strong, but they're somewhat muted. Yeah, but they're still the same. Qualitatively, we see the same patterns.
So I have a quick question before you move on.
Yeah.
So in your literature review, you talked about how the STAR program has been used to study peer effects. And I'm wondering how you, I mean, this could just be me being unfamiliar with this literature, but how can you separate out the rank effects from peer effects? Because, if I rank high, then I have kind of, my peers are less smart than I do. And, if I'm conditional on ability. So I'm maybe off here, but how do kind of peer effects interact with rank in general?
That's a great question. So I would say that if we don't control for the mean ability, so I would say you capture a lot of the peer effects by controlling for the mean ability. I would say if we didn't do that, then what we would do is interpret these coefficients as potentially being driven by those same peer effects. It could be that being a higher rank, these rank effects are peer effects in some way. but yeah, by controlling for the mean ability within the classrooms, you're going to capture some of those peer effects, essentially. Yeah, because what we want to do, we don't want to get the difference, the distance of your score from other people. We just want to get the ordinal rank, essentially. So am I better than that person? And by controlling for the mean ability, we capture that. These are great questions. So to summarize, these results on test scores, long-run test scores, I'm going to find that a decile increase in kindergarten rank is going to increase your rank position in the 8th grade distribution by 1.7 rank points. Denning, Murphy, and Weinhardt, who used the Texas data to show 3rd grade rank effects on 8th grade scores and other long-run outcomes, find a very similar effect, but it's slightly weaker. It's about half the size. When thinking about graduation, I'm going to find that a decile increase in your kindergarten rank in reading is going to lead to a 1.3 percentage point increase in the fact you graduate. Slightly lower than what Elsner is 45, but then again, they're looking at high school rank, so those outcomes are much more contemporaneous. But Denning, Murphy, and Weinhardt find a similar effect size looking at 3rd grade rank. So this might be some evidence that in terms of high school graduation, these kindergarten rank effects are going to fade away relative to newer rank effects. Like I said, I don't find much evidence on these non-cognitive skills, the effect of rank on these non-cognitive skills, but importantly, Murphy and Weinhardt find that these rank effects are going to increase self-perception and confidence. Same thing with Elsner and Isford. You look at high school rank, they find that high school rank is going to increase self-perception and measures of effort. None of these papers look at performance, whether or not these students take ACT or SAT or the performance on those exams. So the results I present here are novel in that respect. So one feature of the STAR experiment is going to allow me to test an existing theory about what's driving these rank effects. So one potential mechanism is that it's ability tracking that is causing these rank effects to appear later on in test scores. So this would happen if schools place high-ranked students in specific classrooms for which they then get this benefit on, let's say, 8th grade test scores. This is going to then cause an increase in performance and outcomes. So a wrinkle of Project STAR that I can leverage to study this is that students are meant to stay in the classrooms they're assigned within their schools until 3rd grade. So this is going to restrict the ability of educators at the school or administrators to sort students into different classrooms based on rank. So I'll look at performance in grades 1 through 3. And if I observe these rank effects in 1st through 3rd grade, this is evidence against this ability tracking story. So I'll estimate the previous model as before, but present results for math and reading scores based on math and reading rank from grades 1 through 3. So here, pretty much across the board, rank effects are stronger in 1st grade through 3rd grade and significant across the board. So this is saying that increasing your kindergarten rank in reading, for example, by 1 decile in your classroom is going to increase your 1st grade overall reading score by 3.7 percentage points in the overall distribution. So I would say this is pretty strong evidence to the extent that classrooms were, or educators and administrators were sorting children into classrooms in grades 1 through 3. This is evidence against the theory that that is what's driving these rank effects that we observe in 8th grade. So STAR data are also really good for heterogeneity. They're going to offer me opportunities to study heterogeneity at 2 levels. The student level, in which I'll look at gender, meaning an indicator for whether or not the student's female, race, looking at the effects, differential effects for African Americans, and whether or not the student is eligible for free and reduced lunch for low-income students. After I do that, I'm going to look at heterogeneous student effects based on classroom and teacher level characteristics. So famously, the STAR experiment was meant to study whether or not after the effects of assigning students to small classes. So I'll look at whether or not these rank effects are stronger or weaker based on being a small class. And it's ambiguous to the extent or which way that would go. I can also look at, is there a question? Sorry.
That was an accident, sorry.
Oh, it's okay. Also look at teacher experience, qualifications, which are things that the state can actually influence. So I'll look at, these are potential mechanisms for policy potentially. And lastly, I can look at teacher race. I won't be presenting results on teacher race today. There's a whole kind of subset of analyses that I still need to do for that. So what I'm going to do, I'm going to transition to a table that is going to present the differential effect for these different groups. So it's essentially going to plot the coefficient on an interaction return between your kindergarten rank and these characteristics, controlling for both that characteristic and your kindergarten rank. So it's going to be the differential effect. And I want to point out that negative coefficients for differential rank means that these rank effects are more muted or less important for these groups. And positive coefficients are going to be that these rank effects are accentuated for these groups, or more important for these groups. So looking at female students here, we can see that rank effects are going to be less important for female students looking at math outcomes. So this is going to be your math test score, less important for graduating high school, as well as your ACT math score. This implies that male students are more exposed to these rank effects, or these rank effects are more important for male students looking at your math score and your ACT math score. Looking at African-American students, we see these rank effects are muted or not as meaningful for African-American students across many outcomes, including 8th grade reading, 8th grade math, high school GPA, and ACT composite score. But even for the coefficients that aren't significant, they're pretty much all negative. This implies that rank effects are going to be more important for white students. And the STAR population is pretty much white or black. Looking at low-income students, however, we see that there are some, these are going to be less important looking at the composite score, the English score, and the math score. So broadly speaking, we can say, looking at these results, that rank effects are going to be more important for male, white, high-income, or non-low-income students. And again, I think there's some room to do some heterogeneous analysis to see, are these differential effects driven by nonlinear rank effects? Thinking about, are you below or above the median in your kindergarten college rank? So next, I'll be looking at the role of teacher characteristics in rank effects. So thankfully, the STAR data the STAR project has data on classrooms and teachers, so I can test these potential policy mechanisms. So something that policymakers can change is the size of the classroom, how experienced the teacher is, and how qualified the teacher is. And you can even match teachers of same race to certain classrooms, or of certain races to certain classrooms. So this offers a unique opportunity to test some potential policy mechanisms to see if we can influence these rank effects. So I'll do the same thing here. I'm going to present heterogeneous treatment effect models where I'm only presenting the interaction term. This is going to tell us the differential effect of kindergarten rank on the outcome based on the characteristic. So focusing on the size of the kindergarten classroom, we don't see much until we get to the ACT composite score. This is saying that for smaller classrooms, these rank effects are not as prominent, although these very, very small effects for pretty much every other outcome make us, it's not a very strong heterogeneous effect. Looking at experience or years, yes.
For that interaction term with class size or small, is it just like a binary variable if you're whether or not the class size is below the mean, or is it literally like the count of the class size?
Well, by virtue of the STAR experiment, they had 4 unique groups that you would be assigned to. It's either the small group, the big group, the regular group, or the regular group with the 8. So this is just whether or not you were assigned to the small classroom.
Gotcha.
So it's an indicator. Yeah. So it doesn't look like we can change these rank effects by changing the size of the classroom. Can we change these rank effects by changing the experience level of the teacher? Doesn't really look like that's the case. Somewhat encouragingly, it looks like we can influence some of these rank outcomes by influencing whether or not changing the qualifications of the teacher. This is going to be an indicator for whether or not the highest degree the teacher has is a BA. So what this is going to say is that if you only have a BA, these rank effects are more prominent. So this is going to tell us, we have a couple significant coefficients here with meaningful effects, differential effects. So this is some evidence that in these long-term outcomes, we can mitigate or reduce these rank effects by requiring higher qualifications of our teachers. So this is kind of the first evidence that we have some kind of lever that might interact with these rank effects. Okay, so moving on to robustness, I'm going to perform 3 primary robustness checks. So the first one is I'm going to take these rank effects, or I'm going to take these ranks, and I'm going to define them as the previous literature does at not the classroom level, but the school level, just to see what it looks like. I don't have the results here today, but these rank effects are actually larger when I look at the school level, when I define rank at the school level compared to the classroom level. So that checks out. Like I mentioned before, I only included a linear term of your kindergarten classroom performance. So I want to change that functional form and see if by allowing for some non-linearities in the way that your actual kindergarten performance influences these outcomes is going to change these rank effects. So what I'm going to do here is I'm going to first create indicators, 19 indicators to capture what ventile you are in the distribution of the kindergarten overall distribution. This is going to capture your kindergarten performance. And I'm also going to include indicators for quartics of your kindergarten score. So these are matching what previous literature has done to capture potential nonlinear effects of your actual performance on the outcomes. I'm then going to move on to the study. I'm going to study the role of attrition in affecting my results. I'm going to create an alternate definition of rank that's only going to use non-attriters. What this is going to do is it's going to introduce a measurement error into the rank variable that is going to give me conservative estimates of the effective rank. And then I perform 2 imputation procedures. One is going to be imputing the mean of your kindergarten classroom 8th grade score to everyone who's missing an 8th grade score. That's going to also give me a conservative estimate of these rank effects. And I'm also going to do this multiple imputation method, which is going to preserve the variance of the 8th grade score, but use the data to predict what students' 8th grade score would be. So I want to present now results looking at differences in the functional form of this ability function. So this is going to include just ventiles in the distribution of where you are in the kindergarten overall distribution. This is going to be including a quartic in your kindergarten score. This is going to be combining both the ventile and the quartic indicator. So we see here that for reading, at least, these rank effects are, they change in magnitude, but in terms of significance, they are robust. The story is a bit different for math. For both the ventiles and the quartic, we continue to have large and statistically significant results, but they are reduced quite a bit when we include both the ventiles and the quartic in performance. I would say, broadly speaking, though, that this shows that changing the functional form of this ability measure qualitatively provides the same results as the main results. So focusing on the role of attrition, as I said earlier, about 40% of these kindergarten students left STAR by 8th grade. So Kruger, in his 1999 paper studying effective class size on 8th grade test scores, shows that this attrition is not driven by classroom assignment, as we saw before in the descriptive statistics that provides evidence that that is indeed the case. So in my setting, I do find that attrition is correlated with rank, in the sense that higher ranked students are more likely to stay in the sample. So this presents a problem potentially if the students who had attrited would have scored differently than similarly ranked students who stayed in the sample. So one thing to consider here is that as part of the STAR project and how the data was collected, if you were held back a grade, if you were retained a grade, you were actually dropped from the study. There's no subsequent data collected about you. So it's reasonable to think that there's some relationship between rank and whether or not you're retained. So this is something I'm still trying to wrap my head around, thinking about how I should interpret this fact, given that I do see differential attrition rates based on rank, and that there is this feature of the STAR project that if you're retained, you are dropped from the study. What would need to happen in order for this retention issue or just attrition in general to meaningfully bias my results is that you would have students who are low ranked, who would have scored much higher, who left, low ranked kids in kindergarten who attrited, who would have scored much higher in 8th grade than similarly ranked students who stayed in the sample. So I'm going to address this a few ways. I'm going to first create a variable that's only going to rank students who in their kindergarten cohorts if they don't attrit. So it's only going to use, the rank variable is only going to use information from students who I continue to see in the sample. So like I said before, this is going to have some measurement error in this rank variable because it's not actually reflecting the kindergarten environment, but it's only going to use data for students who I actually have outcome data for. I'm also going to do this mean imputation process by which I'm going to look who's in your kindergarten cohort. I'm going to create the average 8th grade score for students who are in your kindergarten cohort. And if you're missing your 8th grade score, I'm going to give you that average. So this is going to provide a conservative estimate, I would say, of rank effects, because students who are low ranked in kindergarten who then attrit, as I said before, the main threat here is that they would score higher than similarly ranked low ranked students in kindergarten if they had stayed in the sample. I would argue it's reasonable to think that they would not score above average. So by assigning them the average, I'm kind of baking in this attenuation of the rank effects. Similarly, for high-ranked students in kindergarten who attrit, although that's much rarer in my setting, this attrition is primarily driven by low-ranked students not appearing in 8th grade. But similarly, if you're a high-ranked student, that would bias my results if you scored much lower than similarly high-ranked kindergarten students who I observe in the data. So by assigning them the average, it's unlikely that they would have scored below average. So it's baking in this attenuation of the rank effects, which is going to provide me with a conservative estimate of these rank effects. Lastly, I'm going to do a mean imputation method, which is going to do 10 different imputations of 8th grade rank based on the data I have. It's then going to combine them. What this process does is that it's going to preserve the variance in the outcome variable, but also going to introduce some measurement error, which will also give me a conservative estimate of these rank effects. So here are the results. So based on this new rank variable that restricts the sample to students who didn't attrit, I see that the reading rank has, again, a strong and significant effect, but the math rank does diminish somewhat and it's almost marginally significant, but not quite there. Looking at the mean imputation method, what this is going to do is it's going to add about 2,000 students to the data because we're imputing some data. That's going to include the precision. But because of this attenuation, these treatment effects are going to be much smaller. This is less than 1/2 of the original treatment effect for both reading and for math, but still significant. When I do the multiple imputation method, I'm still going to get significant but much diminished treatment effects looking at reading on kindergarten reading rank on 8th grade rank. Similar effect sizes for math, but much less precise. So that's essentially what I have. So to conclude and to wrap up, so I use data from the STAR project to study several outcomes of students' kindergarten rank. So to go over the findings again, I find that kindergarten rank is going to increase long-run academic performance. It has meaningful impacts on test scores. Specifically, increasing your kindergarten rank within your classroom by a decile is going to cause a 1/10 decile increase in your 8th grade rank. It's also going to have meaningful impacts on college entrance exam performance, high school graduation, high school GPA. There's important heterogeneity by gender and race that are going to mitigate some of these rank effects. Also, there's some evidence of some policy implications showing that if we influence or require higher teacher qualifications, these rank effects are going to be less prominent. I'm also going to show that these rank effects are not likely to be driven by ability tracking. And that's it. Thank you very much.
Thanks very much, Derek. Questions that folks may have, jump in.
Hey, Derek, with the teacher qualifications, did you also include do you also have the age of the teachers that are assigned to them?
I don't think so. The only thing similar to that would be the years that the experience they have teaching.
And have you ran that? Because I'm just like, I guess I'm a little bit skeptical, I guess, of, teachers with master's degrees versus teachers with undergrads and, whether or not that mitigates this rank effect versus is it just like, is the mechanism just simply more mature teachers or more experienced teachers, teachers that have done these master's degrees, that have more experience? I don't know. I'm just a little bit skeptical on that.
Yeah, I think, I guess it depends on what your priors are about the effectiveness or just the difference in training. I mean, it could also be a selection thing. There's no random assignment of qualifications to teachers in the setting. So it could be teachers who select into master's degrees, or just, it could be that they're trained differently, or it could be that they're different types of teachers, even independent of the experience they have. Yeah, I would have expected more, given that we do have these differential treatment effects based on qualifications. I would have expected some movement based on experience, but yep.
Yeah. Otherwise, very cool stuff, man.
Thanks.
Yeah, agreed. And sorry if I might have missed this set of results that you presented, that a lot of this being driven by white males, where we know from other labor literature, this notion of sort of competitiveness and relative standing is sort of super important. You have sort of specific evidence where you were able to look at teacher gender and race sort of interacted with particularly this race gender mechanism? Do you see bigger effects for white males on class rank when they have white male teachers as well?
Yeah, I think, I struggled over the last couple of weeks getting that analysis done to the point that I thought it was good, because there are interactions. What I can say is that, so let me go back to the race ones here. So these muted rank effects for Black students, they essentially disappear if these Black students have a Black teacher. So that's the main finding I have in terms of teacher race interactions. That's the one I can tell. Specifically about white teachers, so there are no male teachers in the STAR data. They're all female. So it's hard to tell a story about teacher gender. Yeah, but there's definitely a role. And I guess the unanswered question here goes back to Alex's original question. So I find here that Black students, these rank effects aren't as prominent compared to white students. Having a Black teacher is going to reintroduce that linear rank effect for Black students. So there's a couple ways that can happen. There's a few ways that can happen. It could be this linear one across the distribution. It could be linear at the top, but flat at the bottom. And it could be linear at the bottom and flat at the top. I've tried to do that by replacing the linear rank variable with quantiles, with deciles, with ventiles to see if there's any non-linearity for that specific subgroup for Black teachers with Black students, but there's not many in the data. So it's hard to get at this non-linearity question. But what I can tell you is that for this subset of students, this differential effect, it essentially goes away. This differential effect for Black students compared to white students goes away if you restrict the sample for Black teachers.
What about the composition? Does this matter by the race and gender composition of the class through which you're measuring relative rank?
That's a great question.
Okay.
Yeah, I've seen some recent papers about gender composition in classrooms that might have been using the STAR data. Yeah, I haven't done that yet.
Other folks have any questions, comments? All right, then I'll thank you, Derek, so much. If you want to hang on for 2 minutes to chat. Just a note, we are not going to have a CHEP seminar next Thursday. For those in the economics department, we do have a job candidate, however, coming through next Thursday. We will certainly have an economics talk that happens that day, I believe a bit earlier in the day. However, I of course don't have it in front of me when I'd like it in front of me, but I think it's at 12:45 next Thursday. So yeah, if you're hungry for an economics, Libra economics talk, we'll have one next Thursday. And then when we meet again on the 10th of February, it will be with Steve Mello from Dartmouth, and we'll be meeting in person in the Finch room, and of course have our a Zoom link though available for those who are not in San Diego. Thanks everyone for coming to the talk. It was great to see y'all, and I'll see you again soon.